incidents. Now we shall, having discussed ideal gas mixture, now we shall look at real gases. In real life, we have real gases only. See, basically ideal gases, we have two beliefs. One is that the gas molecules, they don't occupy any volume. And secondly, we believe that the molecules, they don't have any intramolecular forces, which is not true. So there is always some difference between ideal gases and real gases. And see, we suppose we are dealing with LPG in our house. LPG gas we use for cooking, or you use air for blowing your tires, or even nitrogen for that matter. They are all real gases, and definitely that PV is equal to RT. There will be some variation. Okay. So there are some people who have, scientists basically, who found that there is difference between ideal gases and the real gases, and thus they have come out with proposals, the various equations of state for real gases. Like PV is equal to MRT, this is for ideal gas, but for real gas, they have come out with various equations, and these equations for state are based either on their experiments what they have conducted, or on some empirical results what they have got. Hence, we will see those various equations of state for real gases given by various people. And in your syllabus, we have got few, like we will see van der Waals equation. Then we will also see Betty-Bridgman equation. This equation, Betty-Bridgman, has got more number of constants. Van der Waals equation has only two constants for these two terms. One was that volume occupied by the gas molecules, and second is the intramolecular forces. Then you have got compressibility chart. Compressibility chart also we will find out. We will study that, and then we will be able to find out Z, that is known as the compressibility factor. So this way, like by using van der Waals equations of state, or Betty-Bridgman equation for real gases, or by using compressibility chart, we will be able to study the real gases. And thereafter, after we study this theory, we will see some 5 to 6 numericals, because that will enforce whatever you are studying in theory, that is right. And that will make the learning more relevant and more interesting. Okay, so now we shall discuss about real gases. Hello students, now we shall look at van der Waals equation of state. He was a great scientist. I think he was awarded Nobel Prize also for this. Please Google and check out. So that is so important. Basically, that is what I wanted to convey. Like I told earlier, van der Waals, realizing the above mentioned deviations from ideal gas law, proposed the following equation of state for real gas. So van der Waals equation of state is for a real gas, and here he has taken two constants. because he said he found that there are deviations from the ideal gas law. The two deviations are, one is for the volume of the molecules, gas molecules which it occupies, and second is the intramolecular forces between the molecules of the gas. So the equation he proposed was P. Now we know that PV is equal to RT. Okay. So here is introduced two terms, A and B. There are two constants, and these constants are different for different gases. And there is a chart which will tell you what is A and what is B for different gases. We will see that also in our next slide. P plus A by V square. You see, this is V bar square. This is molar volume of the gas. Molar specific volume basically of the gas. Okay, that is volume V divided by n, sorry, that is a number of moles. Okay, V, capital V, that is volume, divided by n, that is the number of moles. You get that V bar, small V bar square. V bar, that is not a molar volume of the specific volume of the gas in meter cube per kg mole. You can see here the units is given as meter cube per kg. Meter cube means it is volume. Okay, then per kg means it becomes specific volume, and now it is per mole also. So that is what I was telling, V divided by number of moles. Okay, P bracket P plus A by V bar square, bracket closed, next bracket V bar minus B, bracket closed, is equal to R bar T, where R bar is a universal gas constant, and P is the pressure of the gas in kilopascals, and T is the temperature of gas in Kelvin. Now we shall look at the constants A and B for different gases. Now you can see A and B. A, like for different gases, they are given air, oxygen, nitrogen, water vapor like methane, carbon monoxide, carbon dioxide, ammonia, hydrogen, helium. Okay, so A, for suppose let us take A for air, is 135.8. Okay, and B is 0.0365. You don't worry about the fourth column, that is ZC, that is at critical properties. C stands for critical properties. Let us not discuss, worry about that now, because we are only just saying this van der Waals equation of state, where we discuss about A and B. These are the two constants. And this Z is nothing but PV is equal to RT. Yeah. So if you take PV divided by RT, should be 1. But a real gases, it will not be 1. It will be somewhat different. Okay, that is what this Z comes into picture. So as I was telling, there are two constants A and B here. So like the interaction force between the molecules, we will consider it as A. Intermolecular forces is A, that is constant A, and B represents the effective volume occupied by the molecules of the gas. So these are the two gases, and this is about the van der Waals equation of state for real gases. And there can be a question on evaluation of the constants A and B in terms of critical properties. In terms of critical properties, you please see this sketch very clearly. See the sketch very clearly, it is given here. This is a PT diagram or PV diagram, you can say, pressure volume diagram. So you have got this bell-shaped curve, and even if you take water vapor also, so you have got something called critical point. And the critical point, the corresponding pressure is known as critical pressure. The corresponding temperature is known as critical temperature, and this is designated by PC and TC here. Okay, subscript C stands for critical, means at that critical point. One important thing what you should find here is, now suppose critical temperature, this line which is passing through that, there is a point of inflection. Point of inflection means here the derivative is 0. You can see the line which is just above the critical point. At critical point it is flat and then it's coming down. Okay. The constants A and B can be estimated based on the behavior of pure substances at the critical point. So basically constants A and B can be estimated based on the behavior of the pure substance at the critical point. The isotherm is constant temperature line passing through the critical point on a PV diagram encounters a point of inflection at TC, PC and VC. So you can see here there is a point of inflection. The line it is become flat. So now at critical point, dou P by dou V at Tc is equal to 0. That is T is equal to critical temperature, or dou square P by dou V square at Tc is equal to 0 as T is equal to Tc. So using that, now taking that van der Waals equation for state and rewriting it, we get P is equal to R bar T divided by V bar minus B minus A divided by V bar square. Okay. So now if we taking this equation and differentiating the above equation twice, this equation what we have written, P is equal to R bar T divided by V bar minus B minus A by V bar square. This I will differentiate twice. Okay, dou P by dou V at Tc is equal to 0. That's equal to minus R bar Tc divided by V bar minus B whole bracket square plus 2A divided by V bar cube. Second differentiation, dou square P by dou V square at Tc critical temperature is equal to 0 is equal to 2RT divided by V bar minus B whole cube minus 6A by V bar raised to 4. So if you solve this equation, you will get straight away you will get values for B, that is V bar at critical divided by 3 is equal to R bar Tc divided by 8 Pc. Okay, hence Pc bar V bar C divided by R bar Tc is equal to 3 by 8. And the critical property of gases are given by table. So please understand, when they ask you to determine the constants A and B, we have to draw this PV diagram, draw this isotherm, and then write this equation, van der Waals equation, and then differentiate it twice, and then try to solve it. So you can see the critical properties of the gases are given here. Again, for the same gases, 10 gases are there, right from air to helium. The Tc is the critical temperature, Pc is the critical pressure and V bar C as a critical volume. Okay, this is specific volume here, and now it is small V bar means it is molar volume, specific volume. So this way you can find out the critical A and B in terms of critical properties. So this was all about van der Waals equation of state. In our next discussion, we will go for the Betti-Bridgman equation. Thank you. Hello students, this Betti-Bridgman equation was proposed for real gases by the scientist, and they have come out with various constants in their equation. The equation is P is equal to R bar T divided by V bar square bracket 1 minus C bracket close in another bracket V bar plus B bracket close minus A bar V bar square, where P is the pressure of the gas in kilopascal, R bar is the universal gas constant, T is the temperature of gas in Kelvin, V bar is the molar specific volume of the gas, and here you have got A, B, C, three constants are there. Okay, so these to find out this A, B, C, these constants, you have got three equations. A is equal to A naught into 1 minus A bar V bar. So I think this is not equal to A naught into it is. Okay, multiplied, sorry, that is mistake. P is equal to B naught in bracket 1 minus small b by V bar, and C is equal to C by V bar T cube. And the five constants like small a, small b, small c, and capital A, capital B, A naught and B naught are given for the various gases in the table. The one thing you have to remember is this Betti-Bridgman equation is not accurate near the critical point. Like let us see the constant now. Taking helium gas, A naught is given, capital A naught 2.1886, small a is 0.05, B naught is 0.01, small b is 0, and C is 0.0040. So using these five constants like A, B, C small, A naught and B naught, for each gas, the table in the table, these all constant values of the constants for all the gases is given. So first you will write down the values of small a, b, c, A naught and B naught, and then using the relations like A is equal to A naught into 1 minus A by B bar. Second relation, B is equal to B naught 1 minus B by V bar, and C is equal to C by V bar T cube. Using these three relations, you are going to find out A, B and E. And then from this A, B and E, you are going to use in the equation for Betti-Bridgman, that is P is equal to R bar T bar V bar square bracket 1 minus E bracket closed, another bracket V bar plus B bracket closed minus A bar V bar square. So please understand there are five constants here: A, B, C, A naught and B naught. So using these five constants, you are going to find A, B and E first, and this A, B and E you are going to substitute in the Betti-Bridgman equation, and you are going to find out the pressure. Okay, thank you. Hello students. Now we shall look at compressibility charts. The chart looks like this. You can see this chart. The chart looks like this. In the x-axis, you have got reduced pressure, that is PR, and in the y-axis, you have got Z, and you have got the different lines, and these are for different TR. Here, R stands for reduced. Okay, reduced temperature. TR is reduced temperature. PR is reduced pressure, and VR will be reduced volume. So here, if you look at this graph, you got 1, 2, 3, 4, 5, 5, 6, 6 lines for different reduced temperature like TR1, TR 1.1, 1.2, 1.3, 1.5 and TR2. Okay, so you have got this line, and then you have got a x-axis, you have got reduced pressure PR, that is right from 0.5 to 7.5, and all these gases, whatever you are in real gases you are having, like methane, ethylene, ethane, propane, butane, these all n-heptane, nitrogen, CO2, water vapor, they all follow this. So whatever is given is well that identifies the various gases, and actually these various gases you can see they are shown by different symbols like dot, a star, triangle, rectangle and all. So they are almost all similar, so all fall on the same lines only for TR1 to TR2. So this is a compressibility chart. uh, Now we'll understand this. So the y-axis was representing jet. Okay, the specific volume of a gas becomes very large when the pressure is low or the temperature is high. When the pressures are low, the volume occupied that is more per kg of gas. Okay, whether the pressure is low or the temperature is high. Hence, it is not possible to conveniently represent the behavior of real gases at low pressure and high temperatures. In order to overcome this difficulty, the property of each real gas are represented by means of a compressibility factor. Hence, the factor which expresses the extent of deviation of the gas from a perfect gas is known as compressibility factor, represented by Z. So Z or Z, whatever you call it, represents the compressibility factor, and we have seen in the chart that y-axis represents Z. From the ideal gas equation, we have PV is equal to RT. Fine. Now, if you divide this equation PV is equal to RT by RT, you get PV by RT is equal to 1. So, this is for ideal gas. The PV by RT is equal to 1 is for ideal gas, but for real gases, the number 1 is replaced by some other number called Z or Z. Hence, PV by RT is equal to Z, and this value of Z can be 1, can be less than 1, or can be more than 1. And if the value of Z is 1, then the gas becomes or behaves like a ideal gas. Okay, but it will not be 1, it will be slightly less than 1 or slightly more than 1. Hence, these are all real gases. The compressibility factor of a perfect gas has a value of unity under all conditions. As the pressure is reduced, the real gas behaves like an ideal gas, and hence at low pressure for any gas, compressibility factor tends to be unity. Okay, the limit of Z when P tends to 0 is equal to 1. The value of Z for real gases is finite, and it may be lesser or more than unity depending on the temperature and pressure of the gas. This we can see from the table. Now we will come to the compressibility factor. Now in that chart we have seen reduced pressure, reduced temperature. So from where you got that? That comes through the compressibility factor. The values of compressibility factor of any gas may be determined experimentally, but the values can also be determined using the properties of gas based on the limited data available. This is known by describing gases in reduced properties, namely reduced temperature, reduced pressure and reduced volume, by dividing the pressure by the critical temperature. Okay? So whatever properties are there, if you want reduced temperature, means you will divide the temperature by the temperature of that gas, particular gas at critical temperature. Similarly, reduced pressure, you can see the equation, reduced pressure PR is equal to P by PC, means given pressure divided by the pressure of that gas at critical point. And reduced volume PR is equal to V by VC, that is reduced volume is equal to V divided by Vc, means the reduced volume at critical point. Okay, so you can see here uh, uh, Vr is equal to V by Vc. We can write V divided by Vc. I will write as RTC divided by Pc. Okay, again using ideal gas equation, PV is equal to RT. I am only writing V here. So instead of V, I am writing RT by P at critical point. That is V into rearranging this equation, Pc comes on the top, V into Pc divided by RT Pc, RTC. Okay, here R is constant. The compressibility factor of any one component substance is a function of only two properties, that is temperature and pressure. Here you can see R is constant here. Okay, specific volume is also fixed for that particular gas. Now critical pressure and critical temperature vary. So reduced volume Vr is a function of Tr and Pr. This is known as law of corresponding states. Okay, so you can see here Z is equal to, Z is a function of Tr and Pr. So this compressibility factor Z is a function of Tr and Pr, and this is what is shown in this graph. Z is a function of reduced temperature and reduced pressure. So if you know the reduced pressure, the line, straight line you will go, and then where it intersects the reduced temperature Tr, then draw left, you will get the Z on the y-axis. As simple as this. You have to calculate Pr. So once you calculate the Pr, then draw the straight line at the given Pr. Say it is 4. So I will draw straight line at 4, reduced pressure. Then suppose if Tr is 1.5, then let this 4 interact at Tr is equal to 1.5, and then draw the horizontal line. You will get as Z is equal to 0.8. In this equation, for a reduced pressure of 4 and reduced temperature of 1.5, you will get the value of Z as 0.8. So this is what is the law of corresponding states. Okay. So using these relations like reduced temperature, reduced pressure, we are going to find out the value of Z, and this is nothing but a compressibility chart. Okay, so we have seen now by van der Waals equation, Beatty-Bridgman equation, and this compressibility chart. Using these three relations for real gases, we will find out the various states like pressure, temperature of the real gases. Thank you. Hello student, now I shall look at few problems on real gases. We start with a simple one. Like determine the compressibility factor for nitrogen at 10 megapascal and minus 80 degrees centigrade, and at 0.5 megapascal and 35 degrees centigrade. So here we have to find out the value of compressibility factor, that is Z. Okay, for nitrogen gas, they are given two conditions. One is pressure is 10 megapascal and minus 80 degrees centigrade is the temperature, and second condition is pressure is 0.5 megapascal and the temperature is 35 degrees centigrade. So now you have to go to the table for this critical properties, because to find out the compressibility factor, you have to find out the reduced pressure, reduced temperature. Okay, so to find out reduced pressure and reduced temperature, we should know the critical properties, and thus we will go to the table for nitrogen. Okay, now you can see uh, the now this is a table for critical constants. Now you can see the table for nitrogen, that is third row. Nitrogen critical temperature is 126.2 degrees in Kelvin you can say, and the critical pressure is 3.398 megapascal, and the critical volume is 8.99. So from the table of critical constants, what we have seen for nitrogen, critical temperature in Kelvin is 126.20, critical pressure is 3.398, and the critical volume is 8.99. So these three we are going to use in this to find out the reduced properties. And from the reduced properties we are going to use the compressibility chart to find out the critical compressibility factor, that is value of Z. So Tc is equal to critical temperature 126.20 Kelvin, critical pressure is 3.398 megapascal, critical volume is 8.99 into 10 raised to 2 meter cube per kg mole, that is molar specific volume it is. Now first condition, at 10 megapascal pressure and minus 80 degrees centigrade for nitrogen. So reduced pressure PR is equal to P divided by PC. Here pressure is given as 10 megapascal and PC is also in megapascal. Okay, so there is no need to change any units. So both are in megapascal. So 10 divided by 3.398, we get the reduced pressure as 2.493. This is a reduced pressure. Now reduced temperature. So reduced temperature is equal to T by Tc. Okay, the temperature given is minus 80 degrees centigrade, whereas the critical temperature is given in Kelvin. So both we are converting in Kelvin. So minus 80 plus 273 divided by critical temperature 126.20. Sorry, it is not 30, 20. The reduced temperature is 1.528. Okay, so reduced temperature is 1.528 and reduced pressure is 2. So now you can see here using this table. This is very important. We have to understand how to use this. I think I will show you. Now reduced pressure 2.5. This is a 2.5 line. So I will draw this line like this. Okay, and the reduced temperature is 1.5. You can see the reduced temperature is 1.5 here. So this is the point. Okay, then I will take it left. So it is slightly above 0.8. You understand? So first we will take the reduced pressure 2.5. Then we will take this line. This is a reduced temperature line 1.5. Okay, wherever they intersect, this is the point where it is intersecting. Then I will go to the left and coming to the this is G, this is G or the compressibility factor, and here it is shown. So the 1, the intersection point is 2, and this is 3. This way you can find out the compressibility factor, that is the value of Z. So you can see here the referring compressibility chart for PR and TR. Okay, so PR is 2.5, TR is 1.5. You got Z is equal to 0.84. Now next, for next condition is 0.5 megapascal and 35 degrees centigrade. So again 35 degrees you have to add 273 to convert it into Kelvin. So reduced pressure is 0.5 megapascal divided by 3.398 megapascal. You get is 0.147. You should always understand that units on the top and bottom should be same. You can't put one side kilopascal, one side megapascal or bar. That uniformity of units has to be maintained. Second, reduced temperature is 35 plus 273 divided by 126.20. You get as 2.44. Now you can see here, here the reduced pressure is 0.147. Reduced pressure is 0.147 and the reduced temperature is 2.44. Okay. Now we shall see the compressibility chart. Now you can see 0.144 reduced pressure means it is very close to this. It is very close to. So it is very close to the this value near to 0, 0.14, because next is 0.5 only. So this is the line. Okay, this is the line which is nearing 0.144, that is reduced pressure. Now the reduced temperature was 2.4. So reduced pressure will be some, now it have gone up to 2 only. So you take here, so the reduced temperature is this. Okay, so first I have taken reduced pressure, that is 0.144. Then I have taken the reduced temperature, that is 2.44. The both intersect at this point. So this point is nearly 1. This point is nearly 1. Okay, this is the value of Z. This is the value of Z. So now you can see in this problem what he has told. From the compressibility chart, Z is equal to 0.99. Z is equal to 0.99. So what you understand from this numerical, if the reduced pressure is very low, if the reduced pressure is very low and the reduced temperature is very high, then the gas behaves like an ideal gas, because Z is almost equal to 1 here. Okay. So this is the takeaway from this numerical.